The next thing they specify, is the mask. So every standard has a frequency mask. What is a frequency mask? Basically, on the x-axis we have frequency. On the y-axis we have the power that you can transmit. So at the central frequency, you can transmit whatever power you can transmit, and that number is given by FCC, maximum power transmitted. We call it 0 dBr. Here dBr, R simply means relative. So let's say you decided that the maximum power allowed by FCC is, if I remember correctly, it was 23 or some number dBm, right? 33 dBm with everything else, EIRP and all that. So that would be 0 dBr. Right? That is the baseline. Okay. Minus 20 dBr means 20 dB below that number. Then you have to come down. Basically, at 1.1 gigahertz above the central frequency, you have to come down by minus 20 dB. Okay. So let's see here. So up to 0.94, you can have full power. Between 94 central frequency plus 0.94 gigahertz to central frequency plus 1.1 gigahertz, you will come down in power like that. And then after that, it will be even less, and so on and so forth. Okay. So you can see that even though the band given to you is only 1.76, which really is somewhere here. So basically what happens is, generally I would have expected that this would be 1.76 right in the center. This much. But this is more than 1.76. So this rest of it is overflowing into the neighboring channel. All right. And so you try to minimize the neighboring channel overflow, and that is done by specifying that you cannot be more than this amount, So by this time, you have to be minus 30 dBr. And minus 30 means 1,000 times. Minus 20 means 100 times, and so on. Right? 20 dBr is 1/100th in non-log scale. So they specify a mask like this, and when they design it, basically what happens is, even though subcarrier is just, we show like a straight line here, impulse. Subcarrier is not an impulse. Actually, what is a subcarrier is a square wave of some kind, and therefore it has a frequency spectrum, okay, which overflows, except that it is designed such that the power is 0 at the next subcarrier. Okay, actually I might have a picture. I tried to draw a picture. Right here is the picture actually, which explains that. So let me explain this. So the subcarrier, even though we show it as an impulse, it's not an impulse. What it is, it's a square wave. A square wave in time has a frequency spectrum like this, where there is a peak, and then the period is 1/t. I mean, of this wave, it's not it's a sine wave, so there's a frequency, but at 1/t, it is 0, and then again, it is 0 like this, and it slowly dies down. So when we do OFDM, what we are doing is we are putting shapes like this. I haven't put it. You put many shapes like this, such that the next one will have the peak at this point, where this is 0. And similarly, the next one will have peak here, peak here, peak here. So at wherever the carrier has a peak, every other carrier has a null. That's to make them orthogonal. That's what makes them orthogonal. Okay? Orthogonal means that the spacing between the carriers is exactly 1/t in the frequency domain, where t is the pulse time. Okay, so now using this OFDM, if we know the spacing, we can figure out how much bigger pulses, how many big pulses we can send without violating this orthogonality. So, you see, if you're going to send the pulses of time t, and then you have a guard interval or cyclic prefix, then you will need to have that much frequency spacing. Okay, and the frequency spacing is inversely proportional to the pulse time. Okay, so let's see, we finished everything here. Yeah, similar marks exist, and dBr is decibel relative. dBr. So relative to this is the baseline, 0, and then this is 1/100th of that and 1,000th of that. By the time you reach 4.4 gigahertz, minus 2 to plus 2.2, you should be 1,000 times in the power level, 1,000. Okay, all right. So let me just ask you about this thing. HRP Transmit Mask is somewhat clearer now. I mean, you have to read that paper, by the way. If you don't read this, you won't get the whole thing. But if you read that paper, then you will see this mask, and it might be clearer. But the idea is that power level is specified like this. Power distribution is specified. So when you design a device, it might be taken to a lab, and then there they will measure the power levels. If it is any outside of this, then you are not following the standard. And if nothing else, now you know what is dBr, decibel relative, and you know that how they keep decreasing the power slowly as you go out of the band. So this slide, which we are somewhat kind of finished, was that there is a relationship between time domain and frequency domain, and which is by this, is that in the frequency domain, whatever you selected as the frequency spacing becomes the symbol duration, and becomes basically the FFT period. So FFT period in this diagram, when we came time with duration, FFT period says is 1 upon DFSC, and DFSC is 4.957 megahertz, right? So if you do 1 upon 4.957 megahertz, you get 201.73 nanosecond. Okay, that is the FFT period. That is the width of the data part, capital T. Capital T, this we call capital T FFT. Now the question here asked was whether FFT period is same as FFT duration. I mean, maybe we can say that they are same, but then there is symbol duration which is different. Okay, so now what is symbol duration? The symbol is longer than T because we send a pulse and then we leave a gap. Okay, that was the guard interval. So the symbol is so long and the FFT part is so much. Now, actually, we don't leave the gap. What we do is we send something anyway and hope that it will get there. If it doesn't get there, there's no big problem. But there's no point in leaving something unused. So that time is used, and we call it cyclic prefix. So cyclic prefix is basically, we have some information that we compute based upon this data, and we put some of it in the front, some of it in the back. And if the symbol gets shifted, as it will, and some of that cyclic prefix will be lost, but whatever of the cyclic prefix is left over will help us reduce the error in whatever we have received. Okay, so these cyclic prefixes are the error correcting bits. Some of them are lost, some of them remain. You understand? So basically, so there's a FFT period which is 201 nanosecond. Guard interval which is 1/8 of the FFT period. Now why 1/8? So again they discuss how far this signal has to go. If it has to go very far, then of course you need a large guard interval because symbol can move a lot. If it has to go very short distance and the reflections maybe not be that much, in that case we don't need that much of guard. Okay, we could have 1/16th guard. We could have 1/32nd guard. We could have, if it has to go very long distance, then we'll have 1/4 of a guard of the interval as a guard. All right. So this gap is a fraction of this T. In this case, they decided that it has to be 1/8 of T. And so the total symbol duration is so much. So now when you calculate the bit rate available, you will calculate based upon this. In this duration, how many bits can you get through? The key in this slide is that this time is inverse of this spacing. The narrower the spacing, larger symbol time you can send. And that comes from this diagram. By the way, if we increase t to infinity, what will happen on this side? It will be a constant function. And what will happen on this side? This will become impulse, because as you increase t, this will become narrower, 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 and it will become an impulse. Okay? So impulse in frequency domain is unit function in the time domain, and reverse as well. A impulse in the time domain is unit function in the frequency domain, and vice versa. Okay? So when we study about fast Fourier transform, all of this becomes clearer, but we are not going to do that. But at least this is clear that the width of this pulse is 1 upon of that. So as we increase this, this will become very narrow kind of power function in the frequency domain, and it will become an impulse at t equal to infinity. All right, now let's go to the coding. And we have discussed coding, and so, but just to be clear about it. So we have 3 coding. First is this one, the middle one, which is called outer block code, which is read Solomon 224.216. And there are many codes. Okay, read Solomon is just one of them. And so this code, RSN, K, this is a code which tells you that instead of 216 bits, we will send 224 bits using some formula. Okay? Similar to CRC, these bits are calculated using some polynomials. And so instead of sending 216, you send 224. So 216 becomes 224 bits. That is the first code, right? The second code is the inner code. And that is where you send, instead of you basically you send them 2 for 1, or 3 for 2, or 6 for 5, and so on and so forth. Right? And this is in addition to RS. And this particular code has 2 different kinds of coding here in our code. One is called equal error protection, and one is called unequal error protection, UEP and EEP. Equal error protection means all bits are equally protected. So if you have a 156 bit frame, or 100, doesn't matter, 128 bit frame, all the bits are equally protected. But in some cases, you may want to protect some bits more than the other. Unequal protection. And so, for example, you may want to protect a header better than the payload. Right? Or in case of video in particular, in case of video, if you lose the last bit of a word, it doesn't make a difference. The color is, let's say, 9, and you make it 8, it will not make much difference. So the first bit is much more important than the last bit. If you change the first bit, the color is 8 and it becomes -8, it will look odd. Right? So the first bit is more, so they use unequal error protection. With unequal error protection, some bits are protected more and some bits are protected less. So the way they calculate how to add the bits depends more on the some bits more than the other. Okay, so this is all selection, how you select the polynomials. All of these is actually done in polynomials. But anyway, so this is that. And then after everything is done, then we do the modulation, which is when we send on the air, we can use QPSK, 16 QAM, 64 QAM. Right? So there are 3 codes. If you want to call them codes, this is modulation, and these 2 are the codes. And the new thing here is unequal error protection, because we have not seen this in other standards. Okay, this was designed especially for video, and the video people realized that first few bits are more important than the last few bits, so they introduced this UEP.
So its impact on the data rate would just be by multiplying that value by the...
Right. So the thing is, if you do, let's take an example here, 2/3 EEP and 2/3 UEP. Overhead is same. But the video quality with UEP will look much better because the bits that matter are protected more. Alright, so that ends the wireless HD. It is designed for video cable replacement. It has 3 PHYs, high rate, medium rate, and low rate. And low rate is used for discovery and multicast. Everybody speaks low rate. There is a centralized access, although there is no access point, but the coordinator issues the beacons and allocates the reserved transmission slots. And then random access time blocks are used for unallocated transfer. So this is actually RADBs. We had seen them before in 11AD, and we had called something else. They were called in 11AD. They were called CPB, congestion something, CPB. These were contention-based something, contention-based access. So this is the same thing as RADB here in 11HD, sorry, in wireless HD. And channel time blocks, CTBs, are used for pre-allocated transfers. And then power save mode and device control. Actually, so we have skipped some of the details of this. I really wanted to concentrate on that parameter set because that is important to understand. And because we will be using that in later on in LTE and other places. All right, the summary of the whole chapter. 60 gigahertz, also known as millimeter wave, because as we said, 60 gigahertz is 5 millimeter. It has large bandwidth, very small antennas, so you can have lots of antennas, and you can use beamforming at very gigabit at high speeds. Then nowadays you can buy tri-band devices. So you can buy a router which has 2.4 gigahertz, 5.8 gigahertz, and 60 gigahertz. Actually, they are saying are coming, but they've already come. I mean, I checked on Amazon, you can buy a tri-band. And 11AD LAN uses PBSS central control point. So the central control point is there. That's a function which is built into some of the devices. And wireless HD was the previous leader. And in all cases, antenna alignment and tracking is required. So you need to practice the tracking first and then, do the alignment. All right, there's homework number 7. What is the EIRP of the system that transmits at 1 watt using a 10 dBi antenna? So now it is a directional 10 dBi antenna and it's sending 1 watt. So you should be able to calculate EIRP. OFDM system has to be designed using 1 gigahertz band, 5 gigahertz spacing, 5 megahertz spacing. Use subcarrier, size of FFT. Now here I have asked FFT duration, and the question was what is FFT duration? I would change that to FFD, whatever we used before, interval, what was it? Period. Because then we will just leave it FFT period, and symbol duration, it would include FFT period plus the cyclic prefix, and then the data bit rate using all these codes. 3438 inner code, and unless specified, it is always assumed EEP. In this case, I didn't say EEP or UEP, so it is EEP, equal error rate protection. Then here is the reading list. There are 2 books. There is IEEE standard, ECMA standards, and so on. But anyway, I think that's the end.